I have no idea. Yeah. का डेटा है 50 in the 10th को आज कर
Yeah, I can do it. Then afterwards you start deleting. That's okay. Yeah, that's okay. No problem. Connection to. Yeah. Do you have to do any switch here? Send you or connect? What is connected? Laptop as well as. Dwelling on, I'll not be dwelling on what is a shock. I'll jump right into where this becomes important. Okay, so that's what I would see. So this part, of course, you would know. Shock waves are, very briefly, they are waves. They are actually considered as discontinuities across which there is a sudden change of or a jump of pressure, temperature, and so on. You always find shock waves in flows which go beyond sonic speed, right? Beyond Mach 1. And well, they are found a lot in aerospace applications, and uh, they are also found in all kinds of explosions and so on. They have in aerospace applications, of course, they are there in any aircraft. Most of our transport aircrafts also go into transonic regime, so there also you will find shocks. Uh, but what we have been doing in the lab is to look at variety of applications of shock waves besides the mainstream. So this is our lab. So where we have a number of shock tubes, shock tunnels, and we have places where multiple faculty from different departments come together, work on shock waves. While we specialize in generating the shock waves, other members try to apply them into different disciplines. So, yeah, this gives you just a brief of what kind of facilities we have. I hope this has been introduced to you, so I will not go too much into this. But you can come back and ask me, or even if you want to ask me now, anytime you can stop me. All right, and this is our team. I think I think Professor Jagdish has already spoken to you. Professor Jagdish, myself, Sarvanan Nagsheti, we have all belong to the aerospace engineering department, while Professor Arunan, Deepshika, Professor Reddy was also a part of our team, and he's now a retired member, emeritus professor, and Professor Pramod from mechanical, he is looking into energy applications, and Professor Satyam Suvas from materials. And this is a big team of students, researchers, and staff. So all that I show has been done together. It's a teamwork, so no single person can do a lot of experiments like this. So today I will be showing mostly about experiments on unsteady shocks, and these are the different kinds of work that goes on in the lab. So coming to today's presentation, this is taken from two recent works that we have completed. Okay, since hypersonic and supersonic are there, so I will. Dr. Manoj Kumar did the work on unsteady shock oscillation ahead of hypersonic intakes. I'll tell you where they come. And Dr. Pradeep Gupta, he completed a study on unsteady shock interactions inside the divergent ducts of a device called as a supersonic ejector. And that also has a lot of uses, and now we are exploring its use in the energy domain. Okay, so this is the buzzword now, hypersonic vehicle, and especially a scramjet-based hypersonic vehicle. And here, just like you have your normal aircraft, which has all the components of structures, propulsion, controls, and so on. Even so, in a hypersonic vehicle, especially a scramjet base, you will have a propulsion system. But since it's moving at extremely high speed, you don't need, you can convert the kinetic energy itself into the pressure of the gas. That's called ramp compression, and it uses shocks. Therefore, we don't need a lot of, and in fact, we don't need any moving parts. So the scramjet-based vehicle, it follows the same Brayton cycle, but the compression is carried out using uh, aerodynamic means, using only shock waves, and then combustion happens by injection of fuel, and then after that expansion and thrust production by the nozzle. Uh, because all this is integrated into the vehicle, the philosophy of uh, trying to design such vehicles is slightly different from. Uh, okay, are you able to hear me? I think it got it. It's okay. I think I'm loud enough for this all at least. Can you hear me from the end? Yes, sir. I think that's enough. So what I was trying to tell you guys is that the transit vehicle, uh, it doesn't have any moving parts, and while designing this vehicle, it is an integrated task. We cannot separate out propulsion. We cannot separate out because some of these parts this part produce high pressures. So you have higher pressures at the base and a lower pressure at the top, and therefore you can get lift also. So the design of scramjet-based hypersonic vehicle is an integrated task where we have to couple aerodynamic intakes. They have a lot of shock boundary layer interactions. So we find that there is a special, it is not an off-design condition of the intake. In the real design condition, the intake captures the mass, compresses it, and sends it to the combustor. But this intake is very susceptible to something called as unstuck. And once unstart happens, correct mass flow will not go into the combustor. And if it doesn't go into the combustor, you lose thrust. Not only that, we'll show you that it produces severe oscillations of the shock. And the shock is, as I told you, it produces a sudden jump of pressure. If the shock itself oscillates, then it produces extremely large pressure oscillations, which is not very good for the vehicle. So let's go into some of these intakes and what we have done. So there are many kinds of intake. It depends on what the intake, as we said, it is actually designed in an integrated manner. So based on the core vehicle that is getting designed, we can design many different kinds of intakes. Among them, we look at 2D wedge-shaped intakes here because it's easy to look inside the plant. We kind of shape. So we go for mostly rectangular kind of geometry that we need. So when we look at an intake, it is basically we are interested in, since it produces compression, we are interested in the pressure ratio. And not only that, uh, we are also interested in what is called as the total pressure, because the total pressure ratio actually tells how much entropy is getting generated. More the entropy gets generated, the efficiency starts decreasing. So we would like to have as high total pressure ratio as possible. And static temperature is also important because the combustor eventually requires a certain static temperature to be also provided. So these are various performance parameters of an intake. So, and when we look at, as I told you, what is a started intake? A started intake is something which takes in whatever mass it is designed for and it gives it to the combustor. And during this operation, since the entire flow path in the diffuser region, at least in the forward portion, that is in the upstream portion of the diffuser, is supersonic. And we know that supersonic flows do not allow upstream propagation. So downstream changes do not affect mass capture characteristics. Okay. So again, I'm assuming some things are known to you. If you have some doubts over here, you can always stop and ask. Uh, this is a started intake, but these intakes can get unstarted very easily because the flight can go into off design conditions, okay, or you may happen to throttle the combustion chamber and then suddenly back pressure, the pressure after the intake may increase because of such throttling phenomena, and then it can cause certain phenomena to occur by which you then take the goes to unstuck. And a very conservative limit, this is from a geometry perspective, uh, that tells what should be this minimum area at this diffuser such that the intake always stops. Okay, it is given by this Cantor's limit, and I will explain to you why that comes by. Okay, so if you consider an ideal diffuser, this is an ideal supersonic diffuser, and it's completely isentropic. There are no shocks. Okay. Then, if it is going to convert a supersonic flow into a subsonic flow, then we have a minimum area, and we expect that the minimum area will contain the Mach number 1. Okay, and this is uh, the choking phenomena in waiting area ducts of supersonic flows. Uh, Now, um, what happens if, due to some reason, a shock appears in front of this duct? Once we have fixed the duct, so usually the designs usually fix the geometry. So once the geometry gets fixed, and during the flow, suppose a shock appears over here, then we run into problems because a shock produces entropy, and therefore it, across the shock entropy reduces, and this actually takes you much lesser mass than uh, what it is designed for. But what we also find is that the contraction, that is the throat area that we get for this condition, is even much smaller if we design according to this ideal isentropic diffuser condition. Then the throat area is so small that this shock cannot get swallowed. So basically, you can design in such a way that the shock just passes through the entire duct. but that is a condition that we have to design for, and that condition is what is given by controls. So you can see there are two curves over here, a dashed red curve and a blue curve. Okay, so the blue curve is the controls curve, where if you have these minimum areas above the controls curve, then the likelihood of an intake starting is always there. It is always starting. While if the area, the minimum area is exposed, it can be also written in terms of the area ratio. Okay, so if the minimum area is below the isotropic line, then the intake will never start. Okay, and in between these two, there is a likelihood of them starting or unstarting. It's called the dual solution story. Okay. So this picture is important to carry when we go and see what we have done and what studies we have carried out. So, shall I move ahead from here? All right. So now, why does this unstart occur? It may occur due to some back pressure increase at this transit combustor, or it can also occur due to change in the very high contraction or the area of the intake getting changed in such a way that the contraction becomes very high. And as a consequence of this, you can have shocks. Actually, the unstarted intake, it actually produces shock waves come out of the intake, and they stand outside the vehicle. And often this is very highly oscillatory. Sometimes this unstart can also be caused by severe shock boundary layer interactions. So shock boundary layer interactions also affect the flow. They affect the way the streamlines go into the duct. And if the shock wave boundary layer interaction produces a very large light entry to the duct, then the flow just leaks out, and that also leads to unstart. And such kind of unstarts are usually termed as soft unstarts, while hard unstarts are more from a geometric perspective. The contraction becomes high. While the unstart itself can produce an spillage. So when unstart happens, what happens is the incoming mass flow is much higher. The intake is not going to take in that mass flow, so it will spill out. It's like an overflow. So the spillage can happen either by a subsonic means or by supersonic means. So subsonic spillage means the shock waves are very strong uh, ahead of this. It has converted high supersonic flows to subsonic flows, and then it will spill. Why? Okay. So a lot of people have studied unstart, but why there are such big oscillations? How to control oscillations? Is there any sort of scaling, either in the frequency domain or the length domain? These parameters are still not understood, and still a lot of people are working on the big unstart in the hypersonic flows, and this is crucial for the design of hypersonic transit-based hypersonic vehicles. So we initiated some studies on high compression ratio hypersonic intake. So you can see this is the intake. This is called the mixed compression intake, because in this there are a set of shock systems which are away from the internal duct. Okay, this is the internal duct. Then this is called the isolator, which is a duct which separates the intake and the combustor, and it holds any shocks that are produced due to some changes in the back pressure at the combustor side. In our experiments, we produce changes to the back pressure by means of a flap or a throttling back kind of system. So in our intake, we have two ramps and two cowl, basically two cowl shocks. So there are four shocks that get formed over here, and so this is these ramp systems provide the external compression, while the cowl system provides the internal compression, and then it goes into the isolator. We have a modular setup. Modular in the sense that this can actually move. Both the cowl can move as well as the flap can move. And these experiments are conducted in the hypersonic wind tunnel at Indian Institute of Science. So we can actually move these flaps and cowls during the test time of the wind tunnel itself. Okay. So that is called as movable flap and movable cowl system. So we have runs in which we might keep the flaps at a certain angle and see what happens to the flow, or we can move it during the experiment. It's called dynamic flap or dynamic cowl. Okay. So this is a photograph of the whole setup. This is a 0.5 meter hypersonic wind tunnel in University of Science. Okay, and the Mach number we are using is Mach 6, and Knox numbers are of this range. Okay. And for this, we need stagnation pressure, and we also have to keep the gas because when you expand the gas to such high Mach numbers, the temperature is reduced very low. So, in order to prevent liquefaction inside the tunnel, we heat the gas. So, this shows all the conditions that we need to give so that it generates a very good Mach 6 flow. And this Mach 6 flow is meant to go uh, the over the model. So now I told you that battery low. We do a lot of flow visualization. So what is intake height is given here. So I mean isolator height is about 6 seconds. Okay, isolator height is 6 mm. This height is about 40 mm, the total height of the duration of the it's about 6 seconds of test time. There would be about half a second of starting and stopping. Transitions. So basically we use Z-type film engines. I hope Z-type film is has been explained to all of you. And what we wanted here is to study the unsteady aspect of these flows. So that means we need to sort of freeze the flow. Otherwise, while capturing the flow, if there is something moving, you can see if you try to photograph a road in a dark night, you will find out that if you take a photograph, you will see all lights streaking. Why? Because you have moving cars and they are moving at a speed much faster than your shutter speed. Therefore, the exposure is very large. Within the exposure, the object has moved, and as a consequence, you get what is called as motion blurring. Okay, so we have to cater to that. We have to see that there is no motion blurring. Therefore, you have to use some special instrument. Here we use a nanosecond pulse laser light source for Schlieren and shadow. So it's a now non-coherent laser light source, and it pulses can go up to 1 megahertz. But the important thing here is each pulse has a duration of 10 nanoseconds. So we can expect that during that 10 nanoseconds, even though the shock is actually moving very fast, in the 10 nanoseconds, the motion is extremely small, and we have frozen the flow. And if we do this and we couple this with a high-speed camera, which can go at 30 kilohertz kind of frame rates, then we can capture very nice images, and these images will be frozen in time. Therefore, if you can do a lot of frequency-based analysis on these images themselves. Okay, so we can take the images themselves. There are now techniques available called dynamic mode decomposition and proper orthogonal decomposition of images themselves, and we can get a frequency spectrum from the image, and also know we can get what are these mode shapes, how they actually move around. This was another work in a different context where we did this for a flapping uh, jet, and we showed that using this particular device we are able to capture very accurately the frequency of this particular flapping motion, and we also are able to show that using the microphone. So once we had confidence in using this flow visualization and analysis tool together, then we started looking at what happens in our intake flows. So these are the mathematical constructs of POD and DMD. POD is nothing but a principal component analysis, okay, where we find out from each image, right? So you will get a sequence of image. We convert this into what is called a snapshot matrix, which basically is a matrix consisting of all pixels on the columns, all pixels on the rows, and the columns contain different times, snapshot times. And what we find out what are the most dominant nodes in this particular snapshot matrix, and then from there we can get how each image is correlated to those boards, and from there you can get a frequency spectrum. The problem with this is that while this is very useful to generate some spatial mode shapes and find them which are most energetic and so on, but they don't. Each mode can provide multiple frequencies. So one mode shape doesn't have a single frequency, and but that can be solved using dynamic mode decomposition, where the dynamic mode decomposition is nothing but a kind of Fourier expansion of the images. Okay, and we try to find out what is the frequency which is embedded over here. Okay. So dynamic modes, DMD modes actually they give you a single frequency for a single mode. Okay, so these are methods to generate the frequency information, because we are going to see a very large oscillation of these shocks. That's what we do. So here you have the movies. This is a started intake, and I moved, and that is an unstarted intake. So you can see started intake is this is the internal max 6 flow is going on, and you have these shock waves. They provide the external compression. Then you have foul shocks, which you can see here. The shocks are you can see them as very thin lines, and then you have supersonic flow. We can identify the flow is supersonic because we have a series of oblique shocks running in the back. Okay, but you can see this here. We have raised the flap over here in order to increase the back pressure and provide a kind of throttling to the flow. Once this is done, then this has been pushed to one stop. And here, from the back comes out, and then it follows a very large amplitude of oscillation, where it goes out, then it comes in, and goes out, and comes in. It is extremely large amplitude. Okay. So this is a started intake. So we have varied this flap angle, producing different throttling ratios. This shows what kind of throttling ratios we have seen. And among these, what we found was until about 0.31, we had always started intakes. We always 0.35 and 0.42 belong to the dual solution domain in that spectrum, where we could get started condition or unstarted condition, while the last two is always unstarted.
In the dynamic flap, what was the frequency of
No, no, we didn't move it up and down. We moved it to a certain location.
what was the time duration?
That was about no, less than 0.5 seconds. That happened quickly. So, so you have, so we should see our results in this context of the larger controversies curve, isentropic curve. Where do our results fit? So we can see how they fit here. And as I told you, until 0.31, okay, we see that throttling ratio of 0, when there is no throttling at all, it is well above the controversy limit. So that means it starts. Then we start pushing the throttle, and it's going, and point 2 lies almost on the controversy line, and then 0.31 lies just below the controversy line. So all these three have shown us always started conditions. While those in this kind of yellow color markings, 0.35 and 0.42, what they showed us was they were started when we moved the cowl to this particular position. But if we fix the cowl to this, sorry, not cowl, the flap, if we fix the flap to a throttling ratio of 0.35 and 0.42, and then start the tunnel, then it goes into unstart. So if we have an initial started condition and try to push it to unstart, it remains started. But if we start off with an initial configuration, then it is unstarted. So it is in the dual solution domain. While
Under that condition, actually the controversy criteria itself is not valid.
no, it's not valid. Yeah, it follows in the. It is well below that. It's not in the controversy. Right. Well, actually, controversy is a somewhat conservative criteria.
Steady as you
Yeah, it's a it's not steady. So this actually falls very close to this limit, and hence it is unstandard. All right. So here are some flow features and details. So here we can see all the shocks, oblique shocks. This oblique shock comes from the core body, and this is from the ram, the second ram shock. Here we have cowl shocks. There is a very small separation bubble over here, and then you have a series of shocks that go in, and these are flow features in started condition. They do not change much as long as the flow, the intake is started. So here you find all the three cases where the intake is started. We also had pressure ports. All these are pressure ports. Number P and T is on the top side, P is bottom side, and all of them show started conditions. And you can see the pressure ratio we are getting is around 40. Okay, so this is static pressure ratio. It is about 40. And what we see is because it's a supersonic flow, we are actually changing the cowl here. The flap here. We are changing the flap here, throttling it. But no effect is seen on the this is the characteristic of supersonic flow. While you can see the closest pressure transducer actually shows a small change because some kind of communication happens very close to the plant. But all other transducers they show the same pressure, which is what we expect supersonic flow. So we are fine with the flow physics over here. Okay. Now, if you now start increasing the flap further up, then we fall into this dual solution domain where if we started off, this is throttling ratio DF. DF is dynamic flap. That is case A here. Dynamic flap implies that initially you started off the flow and it produced a supersonic flow, and then you started moving the flap from behind. When that was done and the flap was moved to this throttling ratio of 0.35, it remained started. So it basically remained started, was following whatever was earlier we plotted for throttling ratio 0. The same plots were there. But if the second case, we fixed the flap at 0.35 and then started the flow, and then we found that the pressure ratio was much higher, and we see that there is a strong shock that sort of sits ahead of the cowl here, and it produces a kind of supersonic jet, which is over here on the top side of the wall, while at the bottom side it's a subsonic flow. Okay. And this pressure is much larger than the standard case, so it goes into unstart. And there is actually spillage because from here there is a separation, and basically the cowl shock just comes out and it is no longer attached like what is over here. And finally, if we increase it to 0.42, we see the same case for 0.42 also. So both 0.35 and 0.42 belong to this region of, given solution. So here, this shock actually wiggles. It has a very small oscillation, not very large amplitude, but very high frequency. So it wiggles, keeps wiggling, and um, so then after this, we further increased the flap in our next set of lines. So this pushed the intake into large amplitude oscillatory amplifier. And what we found was that this doesn't happen suddenly. It actually takes quite a time to develop. So it's actually a phased development of this large amplitude unstart, which happens somewhere here after about something like 2 seconds from when we initiated the performance. And then we see this last which is the stage 5. Okay. So how do we recognize this? We can do frequency versus time plot. How does frequency of the oscillation change with time? And it's called a spectrogram. And if we do this, then we find that the frequency actually slowly increases. The dominant frequency increases and becomes large after this time, corresponds to this stage 5. Same way when we push it to 0.69 also. And here in stage 5, the amplitudes are very large. So to give this actually stage 1 to 3 just gets accomplished in a very short time. And then we have a slow rise in stage 4 and then finally to stage 5. And to see that, we zoom down, stage 1, 2, and 3. And you can see these are different kind of oscillations in stage 1, then stage 2, then stage 3. So the intake goes through series of changes. These changes also have close resemblance to what we observed in the previous experiments when we changed it from 0, 0.2, 0.4. We slowly increase it, and we find signatures of those changes here in these stages 1, 2, and 3. We again see, like we saw in the previous case, that one shock comes out, it sort of detaches over here, you get a detached power shock here, and you get a supersonic jet. For quite a long time, this jet stays, this system stays there like that, slowly increasing its amplitude, and then finally it goes into full-blown unstart. So this stage 3 is where we observe this system of this large separation bubble here, a shock from the separation bubble that impinges on the cowl, detaches the boundary layer of the cowl, and this system stays there and starts doing oscillation like this, and then finally it goes into full-blown start. So you can see how the pressure signals look here. They have uh, they have a long crest. I mean, basically the crest is there for a long time, and then suddenly there is a drop, and then again the crest is there for a long time. Then suddenly there is a drop. So this is not like your normal sinusoidal signal. Sinusoids have a very nice shape, but this is a different kind of shape here. That means
it goes and stays at one location for quite some time, then comes inside. Then again goes out and stays there for quite some time. Okay, and from here we could estimate the frequencies both from streaming as well as pressure measurements, and this frequency comes out to be about 474 hertz for this case. Finally, it goes into this full-blown unstart. You can see the amplitudes of oscillation are very high, very large change in pressure, and this has a peak frequency close to about 1000 hertz. So this high frequency as well as large amplitude. Okay, and here what we see is that we get almost a near normal shock. It comes out, and then it comes out, then starts going back inside. So that is the whole cycle that it follows. So this is the case of when we changed the throttle, we see very large amplitudes and start. When we change the cowl, because we had both the flap and the cowl, when we change the cowl, if we change the cowl, it is like changing the geometry of the intake. So we are changing the contraction of the intake. So when we change the contraction of the intake, it can produce and start. And this also falls, we look at it in the domain or in the perspective of these things. We have three cases which fall under started condition and three that go into unstarted condition. Here, because we are changing the geometry, the mass flow rate actually changes. Okay. Mass capture changes a little bit. It reaches a maximum and then in the unstarted flows it drops significantly. And we can see spillage over here. Uh, so in these cases, when we change the contraction for the initial cases, it remains started, okay, and the flow features are similar as what we discussed earlier. But the only thing is, as we kept on increasing the contraction, making it more and more uh, contracted at the throat, at the isolator, then we start seeing some strong shocks coming out from this last pressure transition. But otherwise, the pressure profiles were all similar. So finally, we get into a stage where the contraction is so high. So this actually is more like a straight line, and in this case, the cowl has been bent up actually. So this is slightly to give us this condition of high contraction ratio. When we go into these regimes, what we see is we get a shock system of this kind. So we also did the numerical simulations for these cases. Since we wanted to know what is happening here, it was not so obvious as it was in the previous case of changing the flap over here. The reason is that you get shocks that come out, there is spillage, but there is no very large amplitude motion. They would remain more or less at that location, oscillate there at very small amplitude. So why this is happening? Why this kind of oscillations are happening is what we wanted to know. And what we found from these things are that there is a kind of shock-shock interaction that gets established in front of the cowl over here. And this shock-shock interaction can generate supersonic flows. Okay, and this actually generates a supersonic flow. There is a shear layer, and this shear layer actually impinges on the cowl bone, and it forms a kind of virtual cutoff. Okay.
That's a very instability.
Yeah, very instable. So it forms a virtual cutoff over there. So these frequencies are much higher. They are in the order of around 2000 hertz. Okay. So these oscillations. So then we went on and found out why then these oscillations are getting formed, and this was because of this shear layer impinging on this particular cowl wall over here. This actually generates a kind of virtual cavity, and then you can have, if you have such a cavity, you can have a lot of vortices being produced over there, and these vortices they sort of amplify in the cavity, and then it gets pushed out, and then again the system re-establishes. So, but these oscillations would not be very large in amplitude. So, this is the mechanism that gets done in these kind of oscillations. So, we sort of summed up all of these studies, and what we found was that there are two modes of oscillation. One is very large amplitude, the other is small amplitude oscillation. And this kind of oscillations have been found in other intakes by several other people, and they uh, they have said, you know, we found this particular, we have found this particular oscillation, this is the frequency, but it was never clear where we can draw a boundary, where we can draw a line as to when we would get low frequency oscillations, when we would get low amplitude, when we would get high amplitude. And so we collated all those data and we looked into their steerings, and we found that this shock impingement on the cowl has a very important role to play uh, in deciding what kind of oscillations we get. If the cowl actually, if the shock oscillation actually, you know, it goes and hits inside the cowl side, then we get into this very kind of oscillations, which are very small amplitudes, because here it is mostly dominated by the cowl side separation. And these are small amplitude oscillations, they generate a shear layer and then uh, give a cutoff. While if it is outside, if the shocks lie just outside the cowl, then they produce very large amplitude oscillations. And if they come and sit just at the cowl, it sort of forms the boundary between these two. And we have not only our studies, we have used several other studies and shown that this actually forms the boundary. And also, what kind of scaling does this give? Okay. So this mainly is decided by what is the extent of the subsonic region in this particular flow. So in all these flows, we find that there is some subsonic flow. Okay, it may be small. If you have a shear layer cut off here, the subsonic flow is very small. While if it is not there, if it is subsonic all through, then you have a very large length of subsonic flow. So the length of subsonic flow actually decides the scaling. And if you scale the frequencies according to length of subsonic flow, then we find it takes the value 1 by 4. Okay, so it becomes a constant. We were able to collapse not only our data but several other data from before. So these two are now very important, information that there is this, this we can also use it like a design criteria. In order to see, our intake doesn't fall into a large amplitude oscillating domain. How we should look at shocks and where they impinge on the top. We are also looking at how to suppress these oscillations, and we are now looking at something called a bypass bleed, where we have a bleed which takes out the flow from the main intake, but we also have an auxiliary intake where this actually takes it out during the unstart, and we have seen that the oscillations get suppressed here. So this is the current work that we are doing. While this sort of completed the study. So this work we are currently now carrying this on, and we have initial promising results of, dramatic decrease in oscillations.
The bleed here, are you taking it out of the test section or you are releasing it to the test section?
We are releasing it to the test section. This is just a sort of concept demonstration. We just see how to further improve this. Okay. Now coming, so this was a study on start large amplitude oscillations in on start of hypersonic intake. We also observe very large oscillations when we have a device with a supersonic intake. Now this is a passive device. It's used for compression, and in this there are again no moving parts. It's completely aerodynamically designed, and it uses a primary flow which will be of much high momentum. And high momentum primary flow actually entering the secondary flow, mixes with it, and then finally compresses it. And it's used in several applications. A large number of applications use these supersonic ejectors. And these supersonic ejectors also have these two regimes. They have what are called as critical flow regime, and they have what are called as mixed flow regime. In critical flow regime, the jet, the supersonic jet, actually produces a virtual flow for the secondary flow, and it chokes it over there. While in mixed flow, the secondary flow remains subsonic. So the maximum mass flow rate of the ejector is obtained in the critical flow regime, and in many applications, particularly when we look at something like anodic recirculation, energy-based application for refrigeration systems, supercritical CO2 power cycles, these kind of energy applications of ejector need the ejector to work in the critical zone, in this particular zone where the mass flow doesn't change. So we have carried out experiments in our laboratory to look at these. So this is a special ejector test facility that we have built in the laboratory. It has primary flow, secondary flow is taken through the ambient, and the mixed flow is taken out, and so on. So now we can see here what we have observed in our laboratory. There are two flow situations. This is the critical flow where the flow becomes completely supersonic inside the ejector. This is the primary flow, and here we have shocks. These are recompression shocks that come in the diffuse, in the divergent portion. While this is a mixed flow where the secondary flow remains subsonic, this portion is subsonic and everywhere else it is subsonic. So if we see how the entrainment happens, we find that in the critical flow regime, the entrainment becomes constant, while in the mixed flow regime, the entrainment is very strong function of what is the back pressure. And even the pressure profiles in critical flow regime and mixed flow regime, they are quite different. So in mixed flow regime, the pressure increases rapidly, while in critical flow regime, first there is a decreasing pressure and then there is an increasing pressure. So we are interested in this shock oscillations that occur in the critical flow regime because a lot of devices use this critical flow regime, but the shock oscillations can produce unsteady loads on the structure. And these are again high-speed steering images, and you can see these shocks move around, and they move around quite rapidly. Okay, and here you can see the boundary layer. The boundary layer gets separated, reattached, and then so on. These shocks keep dancing around different places. So now we wanted to understand how this, these shocks move. Why do they have certain motion of this kind? So what we do take out uh, the variation of this shock location from images. See, so this is shock extraction. We did image processing to extract the locations of shocks from here. And also we can extract the location of shock from the increase of pressure. So this is called pressure increase method to look at shocks, the location of shocks. So the shock location versus time can be plotted using both these methods. And now we can do our POD, DMD and so on. What we find is there are several frequencies in these motions. They range from 90 to close to 350 hertz. It's multimodal. It's not a single mode is not there. Okay. Similarly, DMD shows us 90 and 350. So both POD and DMD show similar frequencies, as well as pressure signals. They also show us similar frequency ranges, 90, 200, 183. All these frequencies are there. So now this is a bit of it's a puzzle because why is this happening? Why are you getting so many different modes? This multi-mode. So we looked at how do frequencies change with time. Okay. If we do that, to do that, you need to understand frequency with time. When we do a simple Fourier transform, it converts the temporal information to frequency domain information. You lose the information on time. You don't know when a certain frequency occurs with time. So if you want to do that, you need some other analysis to be done. So we did wavelet analysis on the signals, and then we found out that see something like a 90 hertz doesn't occur all the time. It occurs at some instance of time. There are some frequencies which occur for most duration of time, something like around 200 hertz, 150 hertz. They occur for many durations of time. But a particular frequency doesn't last for a long time. Okay. So they come out as you see over here. Some frequencies like 200 hertz, 150 hertz, they appear for a long duration of time. So we sort of try to see, can we find out what is that particular mode shape when the frequency is say 150 hertz or when it is 200 hertz. So what we can do, we have the locations of shock at a particular instance of time. We also know what are the frequencies at certain instance of time from this. We can use both this information and try to find out what is the shock shape at when the frequency is 160. And interestingly, we find that using this kind of analysis as well as EMG gives us the same shock shape. So that means there is some correlation between the shock shape and the frequency. And what we found was the frequency is linked to the distance between the shock cell spacing. And that's because there is going to be these separated boundary layer regions, which are subsonic in nature. And they actually can allow interaction between these two shocks, and that can set up a kind of standing mode kind of thing, which basically sort of decides this frequency. So if we scale this according to the shock cell distance and the upstream velocity, then we see again the frequencies, actually the scale frequencies follow, they all line up together, and it shows a constant which is around 4.5 or so. Okay. So what we found from this is that this shock cell spacing plays a very dominant role in deciding what kind of frequencies we get. So when the whole shock is moving up and down, the shock cell spacing keeps changing, and that's how we get this multiple modes. At different locations we get different. So at 160 hertz the shock is at some location, at 200 hertz it's at a different location. So that's the way we get this. So I have well, today's talk I have discussed two kinds of unsteadiness of the shock. One is in intakes, which is in the hypersonic domain, which is Mach number is 6, while the other one is in supersonic domain. Here the Mach numbers are more in the range of 2, 1.5, 2, and so on. Okay. While in supersonic flow, this is completely an internal duct problem. The hypersonic intake start is a fixed kind of problem where there is some duct and something that's happening external to the duct. So what is interesting in all these things is that the information about these oscillations we have to gather from multiple resources. It's not just one. We have to use high-speed tuning. We have to use pressure measurements, and then gather information from multiple sources, and then try to build what happens to the flow. Okay. So with that, I think I have completed my talk today. If you have any questions, you can have a discussion with me. And thank you for listening.
Does anyone have any questions?
Yes.
In the frequency spectrum, I was expecting one fundamental with multiple harmonics because you have interference between low frequency and high frequency.
Yeah, so
But we don't see any harmonics.
because here if you look at the way the shock is moving, it doesn't follow. Yeah, this is not moving in a in one one place. That sometimes it's happening on the way and goes back. But what we see is when it is at a certain location, it has changed. And then it goes to another place, it changes. Then it goes to another place, it changes. So what we are getting is, as it moves, when it goes to some location, it establishes some kind of a short-term spacing that gives rise to a picture. But then this whole system is moving from that picture.
Is the time scaling of the images, I mean the frame rate sufficiently larger than the download first frequencies?
At close to 20 kilohertz,
Okay.
and the frequencies we are getting are in the range of 200 kilohertz.
And your pressure measurement is also in the same range?
Yes.
Okay. And regarding boundary layer bleed,
Yeah.
you didn't show any pictures.
No, actually, that actually is a full-fledged, another.
Okay.
I didn't want to put too many, but I have a separate. I
Okay.
recently presented it in Sarod,
Okay.
where I have discussed it in length. But here I just wanted to tell we are working to suppress.
But one thing is you are bleeding from the ramp.
Yeah.
I've done some work where I bled from the sides.
Yes.
So it becomes more two-dimensional. Here the flow would be more three-dimensional.
Yeah.
Because you have asymmetric.
Yeah, so here what we have introduced is slots.
Yeah.
Slot bleed, not a whole bleed. So basically we wanted to test the concept where as of now currently there are not many discussions on a bypass kind of a system for a strategy.
Okay.
But that would become necessary because of many other things also. So if we bleed into bypass, that's the kind of thing.
I have a lot of results we can discuss.
Yeah, sure.
This question is about the ratio specific heats gamma. So we are conducting at a laboratory ground level. So supersonic scramjets can be released at various altitudes.
Yes.
So is there any scaling or sensitivity we need to consider? Because gamma is
The composition of air is more or less constant. For whatever scrambles that we are looking at, the altitudes that they are talking about is something like 30 kilometers, 35 kilometers. So there the composition of air is not changing much. The gamma effect comes when the temperature becomes so high that it changes into dissociation and so on. That is really high enthalpy effects which kick in at very high enthalpy. These enthalpies that we have tested here are not extremely high. They are at medium low enthalpy. So therefore we won't see much gamma effects.
okay. So we can translate the laboratory findings to do the intake design.
Extremely high enthalpies we find even we are studying at and so on, our batch number becomes extremely high, like 8, 10, that kind of batch numbers. But the enthalpy effect we have not done testing as of now. Let me see if I have. Yeah, so here. Yeah, if you mount, if you have a pressure pole, if you have a pole and you take a tube and mount the pressure transducer at some different location, then you have to account for that. You have to you have to see that the holes are extremely small. But here, what we have done is we have taken dynamic pressure transducers and we have mounted them directly onto the wall, and they are flush mounted. So there is no gap that is being. So it is as if the wall is there. So that is not going to.
So what for the dynamic movements? How are those simulated? For the example, the cowl movement and the flaps.
So we have a mechanism. That's why this. We actually want to see the whole intake, including the isolators. But you have these two prongs. Inside these prongs, there are mechanisms to move the cowl.
Don't they affect the overall reading of this one?
No, they are outside.
Oh.
They are not inside.
Thank you. If you have anyone else has any questions?
just wondering about the CFT, what you have mentioned. Can you just put some light on the what is the time scale you use in the you have shown the actually yeah, here.
So what we have used here is an unsteady we use SU2 software and Salar Performance
Okay.
with compressibility correction and so on. And time steps were in the range of I think 10 power minus 8 to minus 7.
10 power
Minus 8, minus 7.
minus 7. How much time generally it took for
It
you?
took quite a long time. One particular simulation took us something like 1 or 2 weeks.
2 weeks. Even
2D, yeah, this is 2D.
only for 2D.
2D itself, because our time step is increasing.
Yeah, that's right.
We had to look for the stability and there are these oscillations captured.
Right. And in point of view, how do you, what's the kind of resolution?
Something like that's about 5 lakh.
What the entire model?
Yeah, not only the model, we had the external domain.
External. Is it sufficient to
Yeah,
2D?
yeah, this is 2D, not a 3D would be required.
Yeah. You are happy with the comparison? Is there any comparison? You have kept it separate?
Compared pressures and they're fairly well.
So for this is for the mainly for the hypersonic. Even hypersonic flows your pressures and
That's what I was telling you. Also, we haven't done high enthalpy.
that's
Say
fine.
high enthalpy hypersonic, then you have constant of gamma. This is high Mach number, but enthalpy is not very high. Therefore, we can continue.
Guys, everyone please maintain silence. Thank you.
It is time for any other questions?
If there's any other questions, a round of applause for the speaker. Over to Aditi.
Thank you, sir. I would now like to invite our chairman, Ramkumar sir, to felicitate our guest.
जो BS को कंसीडर भी कर सकते हो उसके लिए मैथमेटिकल मॉडल डेवलप करना एक आज का लूप याद है जो लेकिन मेरे को फॉर्मूला चाहिए कांस्टेंट बोला याद है कुछ सी से या कुछ सिंबल था जी था उसका अगर मैथमेटिकल मॉडल जैसे कोई
I request all our faculty to come forward for the picture.
You want us to turn?
You come out this side. You come out this side. How about the audience? Okay, remove that side.
Yes, all of us stand. Can you stand?